Hi, you know those times at work when you are deeply engaged into a coding task and you just can't remember the next command name? Or that one time when you are texting your friend trying to figure out what will be your next meeting location and you start typing Central Park, and Google just knows exactly where you need to go. So then, when you're finally there, you all start to daydream about your next vacation together. All types of questions are come to mind, and Google seems to know all the answers. So the most important question: when will it be safe to fly, travel, or get married again? And you decided that it's safe, and you hop on a plane and fly to your favorite destination. So when you are finally there, you start asking and thinking, what should I do? And you start typing, what are the best places to go? What will be the weather today or tomorrow or this weekend? And we only type the letter T. And without even typing the whole query, Google seems to understand exactly what we want. Can it read our minds? Well, not yet, but for now we have autocomplete. So search is one of the most important features we have online today. Users have come to expect certain search functionalities, such as autocomplete, from sites and apps like Google, Amazon, LinkedIn, Facebook. And a key advantage of the word prediction is that it helps users arrive to better search results and improve their experience online. Hi, my name is Shani Gershtein, and I'm an NLP data scientist at GE Healthcare. I founded the NLPIL community a year and a half ago, and we currently have over 1,400 NLP practitioners who share their questions and ideas, and we are meeting also on a monthly basis, virtually for now, and I hope soon it will be face-to-face. I'm also a core team member and a mentorship program manager at Baot, which is the largest community of women in R&D here in Israel. So let's start with some fun facts. 3.5 billion, that's the average number of Google searches per day. Mobile devices accounted for 63% of that in the US alone. That's a lot of autocomplete engagement. Autocomplete is especially useful for those who are using small devices. When predicting the next word for us, we won't have to type the entire query. So for both mobile and desktop users, it's a huge time saver all around. And how much, you ask? Well, Google researchers claims that it predicts save 25% of typing time and 200 years of typing time in total per day. That's amazing. So search engine predicts the user query and provides suggestions as they type, without having to type every character manually. The idea that a machine can predict the word for us based on our previous context is really fascinating to me. We can find autocomplete in apps like our web browser, in our coding editor, and Outlook and Gmail application. So how does autocomplete benefit with users? It speeds up the search process. User won't have to type the entire complex query. They will get contextual suggestions to ease their experience online. It will provide successful queries, so no result page is less likely to occur. And it enhances the user experience. It will lead to more enjoyable and higher customer satisfaction. So there are different approaches of implementing next word prediction. In all of them, the steps will be selecting of the language model, data preparation, which includes tokenization, cleaning, and we'll discuss more about it later, and creating the model, and of course evaluating it. So language prediction begins with selection of a model. Language model is a core component for modern NLP tasks. It's a statistical tool that analyzes the pattern of human language for prediction of the world. NLP-based application uses language models for a variety of tasks: speech recognition, spell correction, and summarization. The most common methods for developing next word predictor are n-grams, LSTMs, and of course transformer-based models. Currently, transformer-based models, which use self-attention as a method of language generation and prediction, are the ones most successful in this field. However, these models are difficult to train without a huge amount of data and without a good amount of GPU or TPU. Therefore, I will review the next two options. An n-gram is grouping of n tokens. For simplicity, let's consider n equals 2. In this scenario, n-gram will be called bigram. So in the second row, we can see 5 bigrams. In the sentence either my way or no way, we'll have either my way or no, and no way. We will estimate the probability for the next word given the previous word. After calculating the probabilities for each word, we will choose the best suggestion based on maximum probability. Let's review RNN and LSTMs. These next two examples will illustrate how they are connected. In the first example, let's see what we remember most about Legos. So some of us will say we remember that we built the Lego according to the instructions. Some of us will say that we build it out of our imaginations. Next, there will be a group of people who are always searching for that missing piece. But most of us will remember that they were screaming in agony after stepping on a Lego brick while barefoot. An LSTM network is a type of recurrent neural network that learns dependencies on historic data for a sequence prediction task. RNN model provide a way to not only examine the current input, but the one that was provided one step back as well. Let's review another example. That example will emphasize the need for LSTM. In the first sentence, the grass is always. The next word is simply green and could be predicted by most models and networks. But for the second sentence, it's winter and there has been little sunlight. The grass is always. So here we need to know context from further back in the sentence and to predict the next word as brown. RNN and similar model will be less accurate in this case due to the gap between the context and the word to be predicted. Here is when LSTM will be beneficial, since it has memory cells to remember the previous contents. So LSTM introduced a new structure, the memory cell, and it composed out of 4 elements: the input, forget, and output gates, and a cell state, which is a neuron that connects to itself. The forget gate determines which relevant information from the previous step is needed. The input gate decided what relevant information can be added from the current step. The next step is to decide and store the information from the new state to the cell state. And the output gate finalized the next hidden layer for the next cell. When building our model, the first step will be data preparation. In this step, we will clean and tokenize the sentences, lowercasing it, in order to continue with the model. Next, we will have the embedding layer, which is initialized with random weights and learned embeddings for all of the words in the training dataset. The 2 LSTM layers are followed by 2 fully connected layers. The second one, the last one, is our output softmax layer. And it has the number of units equals to the vocabulary size. For each input, the model will predict the next word from our vocabulary based on the probability. We will consider categorical cross-entropy as the loss function. LSTM recurrent network can be slow to train, and it's highly recommended that you will train it on GPU hardware. It's crucial in the area of deep learning that there is a consideration for the trade-off between model size and performance. Being resource efficient should be the goal rather than improving the accuracy by 0.01%. How would we know if our prediction was accurate? In order to evaluate the performance, we can consider two methods, quality and quantity metrics. Quality-wise, in cases there wasn't any exact matches, it's crucial to look at the sentence structure and the context of the predictions. Quantity-wise, word perplexity, which is a calculation of the exponential of the loss, measure how confident the model is in predicting words. It's actually the quality of the text results, how surprised or perplexed the model was to see the output given the input. A lower perplexity score means that more information about the sentence is conveyed to us. We have a couple of more metrics for the quantitative part. Exact match at n, which shows at which level of probability we are predicting the correct word, if at all, and of course precision and accuracy. We cannot complete sentences with a button press during a lecture or a live conversation just yet. For now, language model can help us while texting or finding information automatically. We talked about language models and how we can use this type of representation to infer the next word. Using LSTM model to capture the previous context of the sentence we would like to complete, and the evaluation metric to measure it before you go live with your next word prediction application. Language understanding and generation practices continue to advance day to day. We are definitely experiencing an exciting time in technology. The work that goes behind the scenes to make your user experience smooth and seamless is enormous. I personally can't wait to see what's coming next. I hope that after hearing this talk, you will see words suggested by Google or your phone keyboards in a new light. I would like to invite you all to join the NLP community, discuss more interesting topics like this one, share your thoughts and recent studies, and network with fellow NLP practitioners. Thank you very much for listening. I'll be happy to answer your questions or comments, and I look forward to seeing you in the NLP IL community.